Okay, so let's discuss a question from fatigue. This is basically design of dynamic loading. Circular shaft is there where you have a alternate axial load, tensile force, which is again varying from 20 kilonewton to 70 kilonewton, right? So it's an alternate loading. So in these kind of problems, what we do is we find out the mean force, which is 20 plus 70 by 2, so which is nothing but 45 kilonewton, and then we get the alternating load, which is the variable load, which you can get max minus min by 2, or you can subtract one of those max or min values from the mean value, the average value. Okay, so this value is 25 kilonewtons. So similarly we get the corresponding mean stress and variable stress. Okay, so Fm by area, which is pi by 4 d square, and which is 45 kilonewtons. So 45 into 10 power 3 by pi by 4 d square is something which I don't know, which diameter I need to find out. So this value is nothing but if I just multiply, so that will be 57.3 into 10 power 3 by d square. Okay, so this is my mean stress. My variable stress, the corresponding variable stress will be the variable load by area, which is pi by 4 d square. So variable is 25 into 10 power 3 by pi by 4 into d square. So this again I can get easily. This is 31.83. Remember, d is unknown, so I will just keep d square in the denominator. 31.83 10 power 3. Okay, so now what is asked is, as per Soderberg criteria you need to design. So Soderberg criteria says that uh, sigma mean by sigma yield plus sigma variable, so by sigma endurance, is equal to factor of safety. So it is something like this. You have on the x-axis you are plotting mean stress, and the limit to that is sigma y as per Soderberg. On the y-axis you are plotting variable, and the limit to that is endurance. And when you join these two, it becomes x by a plus y by b is equal to 1. That is sigma mean by sigma y is plus x by a plus y by b, which is sigma v by sigma endurance, is equal to 1. Now if a point is, if your stress state is such that it's outside, then it is a failure. If it is inside, it will pass as per Soderberg criteria. So that's why we have, for the inside points, if you draw a line parallel, okay, so that line will have some FOS, and that is given by this equation. So FOS will be 1 when the point lies exactly on the line, but if it's somewhere inside, then you have to use this equation to find out. So sigma mean and sigma variable you get from the loading, and we have already found out that sigma y is already given 550 MPa, and sigma endurance, it is said that it is half of the UTS. UTS is 1000, so it is 500. So left side we know everything, right, except the diameter, and right side factor of safety is also given. Basically we need to find out, for the given factor of safety, how much is the dia. So factor of safety is also given as 2. So now sigma mean, let's put 57, substitute everything in the left side of this equation, into 10 power 3 into d square. Okay, and sigma, remember the stresses I am substituting in MPa and forces are Newton, so diameter automatically you will get in mm. So sigma yield is 550 MPa, and variable stress is 31.83 into 10 power 3 by d square, that is the variable stress, and yield is endurance is strength is 500. So left side I have everything, and factor of safety is d. So this is one equation where d square you can take out common from the left side and calculate, and you get d as 18.32 mm. So this is the solution 18.3. So this is a simple problem. Only thing is you should know what is the Soderberg criteria and how to use it and what each of the terms means in this. So 18.32 mm is the answer. Thank you.